Last time we were still learning about like implementing objects, but at this stage, most of it's probably come into place. But we'll carry on again. I finished by talking about remove, but we'll start here again. So let me remember to switch my screen. Okie dokie. So remove. There's a lot of ways to go about doing this, and I'm going to show you an example of where we're going to make use of the equals method we wrote for the student class. Is this necessary? Absolutely not. If anything, perhaps my example here is rather overkill, but I'll show it to you anyways. So I'm creating the function remove, and it takes a student number. The choice of student number, I mean, we could make this whatever we want, but for our case, the student number makes sense because student number should be unique among students. And then I'm going to do a linear search for that student. So for I, 0 to the number of students, if we find that student at location I is equivalent to the dummy, well, then we found it. An alternative here is instead of having the dummy, I could have just said like, is this equal, like, is my class's student number equal to the student number I'm looking for? That would be just fine. But I did it here with the dummy variable. So if I find it, I'm going to delete it. And then I'm going to put the thing at the end, because at this stage, I'm going to draw. At this stage, we have a case where perhaps this was pointing to this student. So we deleted it, but we now have this gap because this is pointing to a student, this is pointing to a student, and this is pointing to a student. We have this gap. What are we going to do? Well, the easiest thing to do is to then say, okay, instead of this pointer pointing at the thing we just deleted, you're going to point at the thing the last thing points at. So there's like this object here. And then this here, we'll just say, okay, the number of students we have is -1. So in this case, as far as the course object is concerned, this cell right here, this array index, doesn't have anything useful in it. So the next person we add will have a pointer in this spot point to the new student. But this would be after the next add, of course. And then here, because I guess I'm saying, well, we'll have it return true if it was successful, false. Otherwise, I guess if we're trying to delete a student that doesn't exist, we would return false. That way the calling code can do some like error checking. And if we ever finish this search and do not ever return out of here, we must therefore not have found it, so we'll just return false. And we don't need to decrease the number of students because we didn't remove anything. So here, I mean, I won't actually run this code, but here's how we would do the test. So this is the same as before, except all I'm doing is saying, okay, remove student number, Bob Smith, or well, whatever that number is, 1, 2. That corresponds to Bob Smith. And then if I print it out again, we should see the same thing. But I'm curious what the order would be, actually. In fact, maybe I will take this code. And here, I'm going to take all this, put this here, paste, and I guess, did I actually add remove yet? Did I include remove yet? Expand capacity, add, toString. It looks like I might not have. So I'm going to go here. I do have remove there. So I'll go back to my code because I'm super, super lazy. Copy this. And I don't know, I'll add it here. Okay. Dummy. It's right there. What are you talking about? Oh, is it supposed to be taking a pointer? Maybe this should be a memory address. Let's have a quick look here. There we go. I guess I had a typo in my slides. I'll fix that. Okay, I'm gonna build this and test it just to make sure it all works. Let me go back here. Ugh. Man, this is taking forever. Okay, let's run it. All right, so the first time we run it, we see number of students 5, James Hughes, Bob Smith, Sally McDonald, Greg Roots, and Sarah Davidson. But then the second time there's only 4, but I mean, you'll see that Bob Smith and Sarah Davidson, like, well, Bob Smith is gone, but Sarah Davidson suddenly becomes the second student, where before they were the last student. This strategy of basically taking the last thing and putting it in the empty slot is only going to work if the order of the things in our collection doesn't matter. And, you know, if we go here and we think for a second, and I know we talked about this last time, what if we think for a second and we have this massively long array, and these are all full of pointers to places and things that are really super important. If I go ahead and delete this one, and let's say this array is like 1 billion long, if I move everyone down 1, that's going to be like 1 million things. That sucks. In fact, that's what we call like an order n algorithm here, because, I mean, the amount of work we're going to have to do in this scenario, if we were to just shuffle everyone down 1, is going to be proportional to the number of things in our array that we have to move. So it grows linearly. If we double the size of this array to 2 billion, then we have to do twice as much work. Where if we have the alternative, can I just undo? All right, I'll just erase all of it. If I do what I'm saying in this particular case, where I've got, you know, a pointer, a pointer, a pointer, and just assume these are pointing to things that we care about, and I delete this one, and then I just say, okay, don't point to this, point to this, how much work was that? Well, regardless of the size of that array, it's like one operation. This is a lot nicer than order n. Order n is sad. This is happy, because this is much quicker. I mean, it takes one step. I don't care if this is 10, a million, a billion, a quadrillion. It's going to take one step. This, it's unhappy because every time I make the size bigger, the amount of work being done gets bigger as well, which is, if it can be avoided, a much better situation for us. But of course, again, this only works if the order doesn't matter. If I deleted the first thing, but the order of the things in that collection matter to me, I might be stuck having to do that like shuffle thing. So, you win some, you lose some, I guess. Okay, here's another function, get number of students. Well, this is easy. Just return the number of students. Easy peasy. Clear course. Okay, so all this one's going to do is basically go through, and I don't care how many students are in here, just delete them all. So we're just going to go through the whole array. Actually, no, that's not true. We're not going to go through the whole array. We're going to go through the array up to the number of students we have in it. Because remember, the maximum size of the array and the number of students in the array can be very different. But number of students must always be no bigger than the size. So we're going to go through each one and delete each one, and then set number of students to 0. So basically in this case, we've got our array. We go to the first one, second one, third one, fourth one. We go to the first one and go, okay, the thing you're pointing to, delete it. 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 Done. And now set the number of students to 0. Awesome. We have to make sure we're deleting. If we were in a programming language like Java, for example, this clear course function, our method, becomes a lot easier. We don't need this. Our clear course could be as simple as this. We just tell our data structure that, like, you know what? I know you're pointing to objects that are important, but because I'm clearing the course, presumably they're not important anymore. So if I just set the number of students to 0, that means as soon as I want to add someone again, it would go into index 0 and immediately overwrite this. So we don't really need to delete it, because Java will also automatically deallocate that memory for us, where C++ will not. Now we can test again. What do I have? ToString, get number of students, clear the course, check it again. If I were to run this, hopefully it wouldn't work. Or pardon me, it wouldn't work. Hopefully it would print out nothing because there's no students there. All right. Now for our copy constructor and deconstructor. You might remember way back earlier in the slides, I brought these up, but I said, you know what, we're going to talk about these later because it's going to be a little easier to wrap our head around these things once we've kind of got the full context of what we want our course class to have. All right, so how should C++ make a copy for us? Because by default, C++ isn't going to know. It's not going to know. We've got like a sophisticated object here. We've got, it's got a pointer to a pointer of student objects that are dynamically allocated. There's a lot going on. We've got a lot of questions to ask. Do I want, like you figure, this is a student object, right? It's got some information, but in it, it's got a pointer to an array, which contains pointers to student objects, right? When I make a copy of this, what do I want that copy to look like? Because I've got a number of choices. Do I want to make a copy and then have that copy take over all the simple values like max array size and number of students? But do I want to just have that pointer point to the same array of students? Or do I not want that? Do I want it to be pointing to a new array, but maybe have those pointers in that array point to the same single students in memory? Or do I not want that at all? And should I be making a copy of the 5 students and then having pointers point to the 5 new copies of those students? I think I messed up my drawing here, but point still stands because C++ isn't going to know. And in this particular scenario, I guess there is technically no correct answer. It's up to you, the programmer. It's up to you because you're the one designing it. You're the one that invented this class. So you're the one that dictates how it's going to act. So we're going to start writing our copy constructor. And I know you're seeing this like constant and course, ampersand. So this must be a reference variable. It is, at this stage, just pretend it's the magic code. We don't need to go into the details of why it needs to be these things at this stage. Basically, it's a constructor that's going to take a parameter that's the thing I want to make a copy of. So I'm actually going to go ahead here. So here's an example of me using the copy constructor. So I've got my course C, which is a pointer to a course. And then I'm creating a new course, but I give it the course I'm making a copy of. So I'm basically saying, okay, here, constructor, here's a course, make a copy of it and put it in here. That's what that means. So let's go back and have a look. So we start it, we write, okay, course, blah, 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 open squigglies. There are 2 attributes that this class has that are very simple. They're just like integers, right? The number of students and the maximum array size, or array max. So all I'm going to say is, okay, so my num students is equal to the object's number of students. So basically, get the number of students that this one has. Get the number of students that this one has, and then also get the number that represents the array max and put it here too. And if we like, you can think of this as having this in front of it to make it clear, like, okay, this is the one that we're creating, and this also, we also have like the one, so this would be C and this would be like D in the example that I showed a moment ago. So this one, by making a copy, it's going to go look here and be like, oh, okay, so I'm going to have like num students and it's going to be equal to whatever this one has. I'm going to have array max and it's going to be equal to whatever this one has. So we take those values. I'm not going to draw those as arrows because that might get confusing. I'm just copying these values over. But now, once we get to the more, intricate, interesting bits, this is where it can get hairy because, well, this is where we're saying, how are we going to do this copy? Are we going to just basically create a new pointer that points to the same one thing or make a copy of the array, but same objects, like same student objects, or copies of everything? This example where we make a copy and then we make a copy of the array and we make a copy of the things that the pointers in the array point to, this would be a very deep copy. this right here is what we would call a shallow copy. So there we go. What am I going to do? Well, I'm going to take my variable, my class, and make a whole new array. Okay, so it's going to make a whole new array, whatever the max size is. And then I'm going to go through for I in the number of students. Okay, so however many students we really have, my class at I, of course we start at 0. So we're right here. I'm going to change my color. We're right here. What should I do? Well, make a new student and, well, hey, look at this. This is actually calling the student's copy constructor. This is the student's constructor, and we'll see that we're giving it a student from object. So we're saying, okay, object, go to location I of your array of students, and then call the new constructor to make a copy of it, and then have my class that I point to it. And we're going to do that for all the way up to num students. So again, this is a very deep copy. And then we're in great shape. That's all we need. So now we've got a complete copy. And you'll see that we basically, in order to make a copy of this, we need to make copies of like the student objects as well. But this is fantastic because we're good programmers. We already wrote the copy constructor for the students. So we can use the student's copy constructor in our course copy constructor. This is fantastic. So we can test it again, yeah. Now, so this would be an example of the very shallow copy where I'm doing this. Let's say this is C, this is D, this is the new one I'm making. I copy over num students, I copy over array max, and I copy over my class, which will be pointing to, so this one will have a pointer, and this one will have a pointer. It's pointing to the same array. So I'm saying this is wrong here because I guess it doesn't make sense in my case. But really, this is a design decision for you, the programmer. And here, this is a similar example, but it's still not like the fully deep copy, because what we're doing in this case is, okay, we made a whole new array, but we're actually making copies of the pointers to the student objects, not copies of the student objects themselves. So this is that middle scenario where, sure, we have two arrays. This one's pointed by the original, this one's pointed by the second, but they all point to the exact same student objects. Now a deconstructor. Again, like the copy constructor, C++ isn't going to know by default how you should go about deleting our course object. How do we do that? Well, the rule is we need to delete everything that we use like the new keyword for. But that's really not true in general, but this is a really good like rule of thumb in this case. So, what are the things, if we go back here, if we look at the course, what are all the things, and another thing we have to think of too is it's not only just where we see new created, it's also, we need to consider who has ownership of this object in memory. And this one's kind of hard to explain at this stage, but once we get to assignment 2, it'll become a lot clearer. But there is an example in assignment 1 where we have to be careful about where we're deleting things. For example, in assignment 1, you've got the like filter by, you've got the filter by country or by continent, right? And that's supposed to return like a pointer to an array. So the method that belongs to the country catalog is the one creating the new array of pointers to country objects. But just because that method inside that class created it, it created it and then returned that pointer to the calling function somewhere else in the code. So it's somewhere else in the code that is now responsible for that memory, where in this case, the course object it's got this array of student pointers, and this is like integral to this thing. Like this array, this memory that was dynamically allocated, it's the responsibility of the course object to manage it. So we see a new here, but you can't just quickly go look at the constructors to know what to delete, because you might say, okay, perfect, I'll just throw in like a delete square brackets my class, which we definitely need to do. But the problem with that is this array of pointers is full of pointers pointing to, or well, at least it could be pointing to a lot of things that were dynamically allocated and still exist. For example, add. In add, we're creating all these new students, and then we're throwing them into our my class, into that array of pointers. So we have to make sure we're going to delete all of the students, and then we can delete our array. Let's have a look at the code. Well, for I less than the number of students, so go through each of these things for as many students there are and delete that particular student located that's gotten to by the pointer at my class at location I. Then at the end we can delete my class. And here you'll see the square brackets because my class was an array. And here we don't see the square brackets because my class at I, well, that's like the pointer to a student. So, you know, it's fine to be deleted the way it is. And I might sound like a broken record, but I'm going to say it again. When we delete something, my class is an array of pointers, and then as soon as we index it, that's getting the specific pointer we want. So when we're deleting like this, although my class at I is a pointer, remember, we aren't deleting the pointers. The pointers stay. We're deleting the things that the pointers point to. It's a funny thing. Some people will hear this and be like, oh, okay, great, I'll remember that. And other people kind of struggle with this. I was one that struggled with this at first too. Hell, every year when I relearn C++, I'm always like, wait, what am I deleting again? So this is something you got to make sure you're remembering, because this could happen where if, let me go back, with remove, here we go. I'm going to draw an example with remove that I know multiple students have or currently still have. They had or still have this problem. Okay? I remove this one, for example. Okay? So here's the student we're deleting, and I don't know, there's a pointer over here, there's a pointer over here. And then down here, there's a pointer to another student. Okay. When I delete this one, so this line of code right here, if I delete my class at I, where I happens to be 0, I go here and I delete this. Cool. Then I say my class at I is going to be pointing to whatever this points to. So, okay, so we're not pointing there anymore. We're pointing there. You might say, okay, well, hold on. We want to clear this one out. If you wrote something like delete, that's a D, at num, I'm lazy, -1. If you were to do this, you would suddenly then say, oh, okay, delete the thing that this points to. But hold on a second. The thing that this points to is the same thing that this new, that index I, 1, or 0, we just updated it to. We just deleted the one single thing that we actually thought we had moved to the front. This is a problem. So this isn't really necessary, by the way, because as soon as we decrease num students, the computer, like C++ knows that this is the cell we're gonna like overwrite next time. But if you really wanted to be super safe and set this to be like, okay, you're pointing to nothing, you would say my class at location num students -1 equals, and then there's a special value C++ has that means like nothing. It is a value, so it is a thing, but it's a thing that represents nothing. It's like in Python, it's the none idea. But in C++, we write this as null PTR for null pointer. C++ also has something called null. Do not use this. We don't like this. We like this. Oh, I heard some questions. Okay, why do we have to dereference if we are not deleting the pointer? Where are we dereferencing? Using delete on pointers automatically invokes the delete method on the object itself, I think. Yeah, that's what it is. But, oh, why do we not need to dereference? Why null pointer versus null? Because null is an older thing that means something different, and null pointer is a new C++ thing that's supposed to be specifically for pointers. We will see this a lot more. Try not to get too hung up on the semantics here because we'll see. And yeah, Felix, Alex and Felix, it knows that, like, okay, delete the thing this points to. It's just why? Because that's how delete was written. It was written such that you don't need to dereference it. So I guess it's smart enough, I guess. Okay, so where was I? Copy constructor, test, copy constructor, yeah, deconstructor. Okay, cool. So let me erase all of my beautiful artwork. And what are we gonna do? Well, yeah, go through each one and then delete the whole class. Fantastic. You might notice that this code right here is the exact same as clear course. So you know what, maybe this is a nicer version of the deconstructor because we're not, we don't have redundant code. Cool. But that's it. Okay, so we're done making our classes here. We've got our student, which is a very simple one. Then we have our course one, which kind of manages the students, and it's a little bit more complex. And we can interact with them as much as we want. And you might still be saying, I still don't see the point of objects. Well, again, it's still about encapsulation, about abstraction. And for those of you, like we wrote the code to add a student to a collection, right? Now, all we have to do is just call add. And you might be saying, yeah, but that's just a function. I know we wrote functions for like abstractions and encapsulation. You're right, but the objects are kind of like a super version of that idea where like all those ideas are now encapsulated within the course object. Why? Well, it kind of makes sense to group all the coursey type stuff together in that one object. And for those of you from Python, if you remember the lists from Python, someone wrote those functions. Someone wrote append. You didn't write it. No, but you used it. Wasn't that nice? There you go. That's the motivation. So summary, headers, those are things. That's where we say what happens, asterisk, because that's going to change a lot soon. We've got our class files. These are things. This is where we say how, again, asterisk. And we made student classes to hold info about students and a course class to hold and kind of like manage the collection of students. And then we interacted with them. Cool. There we go. Awesome. Now, everybody, now I can officially say welcome to 162. At this point, it was just getting us prepared for what actually matters in 162. You may be pleased by this statement or you may be terrified by this statement. Really, you shouldn't be terrified, but it is now we can actually start talking about the stuff that I actually want you to learn in 162. And it's about collections. This is going to be a very high level lecture where we don't really cover much. I'm just going to make sure we have an idea of what we're going to be tackling. So we're going to learn what a collection is. We're going to learn about some of the wording and terminology related to collections. I'm going to warn you that there is a lot of wording that sounds like it means the same thing. And for the most part, we can kind of get away with thinking that they mean the same thing. A lot of times they might have particular nuanced differences, but they're not really going to matter too much for us. We're going to talk about abstract design of collections. Okay, so a collection. It's a group of things we want to treat as this like conceptual unit, this idea of stuff like the lists. A list is a collection. It's a group of information that I just kind of want to like hold there over together because it makes sense to me. Or the course, that's a simple collection. It's it's a group of those students. We want to treat it as this like conceptual unit. Yeah. In computer science, we have very popular collections of items. And the ones that we're going to start with are stacks, queues, lists, trees, and graphs. We will absolutely be covering stacks. We will absolutely be covering queues. We will absolutely be covering lists. Trees, we will get as far as we can, but I am not going to be covering this in a lot of detail because this you'll pick up on next year in second year computer science. Similarly with graphs. In fact, I'm barely even going to talk about graphs. I'm just going to kind of show you what they are and then tell you, look forward to learning about them next year. So a collection, we choose, so we've got a problem to solve. And maybe we want to store our data in a collection in a certain way. But the choice of collection we pick, one, some collections might not make any sense for a particular problem, but some problems might have multiple options. You know, it might make a lot of sense to use this or this. But our choice will have a significant impact on the algorithms we use as well. So our data structures and algorithms are kind of like, you know, yin and yang. I don't know. They go together. They're not opposites, I guess, but they go together. And your choice of one will affect the other and vice versa. Some collections are strictly more powerful or capable than the others. And the way I use powerful here is, never mind. Just let's not worry about that. And now a lot of other people will say like, okay, we're going to start learning. And this happens a lot more in Java, less so in C++ because people are a little less familiar with the libraries in C++. But this one comes up a lot. I will be teaching about a stack, but a list that you've all used in Python. If you took Python with me, you might say like, well, okay, a stack is great and all, but a list is just better. A list can do everything the stack can do and more. But there's two things I'm going to say about this. One, you know, we don't need a sledgehammer to kill a fly. But another thing that we really like in computer science, and this is where computer science starts to get really geeky, is we love to look at all the things we can do with very constrained little things like our data structures. Like this very simple data structure, but what can we do with it? How much stuff can we do with this? Like I know if I grab a spaceship, I can do more, but I want to play with this stupid little thing and see what I can do with it. And that's where we like to have fun. And that's where we learn a little bit about like what the limits of things are, how to get creative with our solutions. And it's going to help with like getting familiar with computational complexity as well. So I know I'm not teaching you stacks because I don't know what lists are. I'm teaching you stacks because they're a beautiful, simple thing that we're going to play around with to learn a lot about. The point of learning about stacks is not because a stack is a super important data structure that you're going to be using 10 years from now in your software engineering job. No. That is, it's such a common meme of like, oh, I learned about stacks and I've used it 0 times since I got a job. Okay, great. But we weren't teaching you stacks because we wanted you to know about this super important data structure stacks. No, we were teaching you stacks for 1,001 other reasons. Yeah, okay. Oh yeah, and then I guess the added point of like, let's have fun with constrained things. And then it becomes really fun where you remove some of the constraints and then see what else you can do. That's a big fun one. So stacks, this is a list of things where we call this like first in, first out, or FIFO, where the first thing that goes, wait, I'm getting this wrong. Last thing, first out. This is LIFO, I guess. Pardon me. A stack of plates at a buffet. A queue is first in, first out. Pardon me. A stack is the last thing that you add to the stack. If you wanted to take something off the stack, well, that's like the last thing you just added, right? Because if I have a stack of, I don't know, things, circles. I've got a stack of circles here. And then I come along and add this one. And then you want to come and take something off the stack. Well, it's the top one you take off. And then there's queues. You've all been in a line before. The first one, or first come, first serve. You know, that's a queue. You know, I think I've got. And then lists, well, we can do whatever we want with them. So here's a stack. I don't know, I guess these are my stacks of plates. I add that turquoise-ish plate. And then if I wanted to remove it, well, this one would be the one that comes off. And then queue, well, you know, people enter at the end and leave from the front, assuming you're following, you know, the rules of a queue. And then lists. And now this is actually a particular example of a list, something we call an ordered list, where the order of things in our lists matter. There might be other lists where order doesn't matter, like a shopping list. It's just a list of things you need to care about. Or the students in a class, they're not ordered. It's just a collection of students. But here, this is an ordered list where if we ever wanted to add something, we have to make sure that the order is preserved. And these are all examples of linear collections, which is like, this is a really fancy way of saying like, if I'm here and I ask you, well, what comes next? You go, well, that thing. I mean, there's like no ambiguity here. If here's our queue, if I'm here and say, okay, who's next? Well, this is the one. And same with the stack. If I say, okay, this is the top one, but then what comes after? Well, this next one, and then this next one. It's linear, it's simple. Like it's got like a straight path, it's easy. Nonlinear, oh, I guess, okay. Each item has a single predecessor and successor, except the edge cases, right? Where maybe I have a predecessor but no successor because I'm at the end of the line. And then there's nonlinear collections. These are things like trees and graphs. I mean, trees and graphs could be done in such a way that they are linear, but they can be nonlinear. So if I'm here at root directory, if I'm standing here and I ask you, well, okay, what comes after root directory? Well, that's not a simple question because it might be documents and settings or program files or my music. I don't know. So what comes next? Well, I don't know. So this isn't linear. It's not as simple as like, okay, 1, 2, 3, 4. It's, I've got a choice to make. And here's a graph. Okay, this is a tree, by the way. You'll recognize it as a tree because we all know trees grow upside down in our world. We call this the root. We call these like the leaves. You know, all the trees you see that grow upside down. And then this is a graph, not to be confused with a plot, because I know a lot of people will learn things like your histograms and bar graphs and scatter plots as graphs. Well, those are like plots. This right here is a graph, a mathematical graph, where we represent ideas or things or concepts as nodes or vertices. The more correct term, I guess, is a vertex, or vertices for multiple ones. And then these lines that connect them, these are called edges. So here I'm kind of like representing a like airports, okay? And the edges are what flights are currently available between the two. I mean, there's probably a flight from Buffalo to New York, but let's pretend there isn't. So yeah, ignore geography issues here as well. Yeah, don't make fun of my bad geography, I guess, in this case. So if I'm in Toronto, if I'm here and I want to get to New York City, well, how do I do that? Well, I guess I'm probably going to want to fly from Toronto to Halifax and then Halifax to New York. So I guess that's how I'd have to do it. I mean, I guess I could go like Toronto to Moncton to Halifax to New York City. I mean, I can get really weird and go like Toronto to Moncton to Buffalo to Halifax to New York. But if I wanted to do this quickly, I'll just do Toronto to Halifax to New York. Collections as abstraction. So we're going to design problems. So we've got problems we want to solve. And you'll probably have noticed so far when learning computer science that we like to represent ideas in the computer, like abstractly. Like obviously when I'm representing a student object, it's not a literal student object. That's absurd. But I've got this like this thing that I'm using to represent a student. Kind of like numbers, how like, well, you know, we use that symbol 1 to represent one thing. It's an abstraction. We separate the what from the how. So what can we do? How do we do it? And we know what we have to do to drive a car, but we don't necessarily know how the car does it. And I use this example all the time, I know. But, you know, you don't know all the ins and outs, all the cam timing, and all the nitty-gritty details of your internal combustion engine. But that doesn't matter. You can jump in your car and you can drive to school and you're in great shape. This idea of abstraction too, it's great for dealing with large, complex systems. And we can deal with each collection of things in a nice general way. And again, we're going to focus on the what, which a lot of times in programming we call the interface. So we separate the what from the how. We want to define what a collection is going to do, because it's also important to remember that these ideas and describing, I just spit all over the place, describing what we can do with this like idea, this abstract idea, and then making use of these things, of this definition of what we can do to solve problems, that is like programming system independent. Think of math. Hell, we can go to something as simple as arithmetic. You know, I can define, maybe we go more complex into like high level number theory, graph theory, I don't know. You know, mathematicians will define what these mathematical objects can do, and they're probably not even programming half the stuff, but it's like based on the definition, I'm allowed to do all these things. So maybe, you know, they work stuff out with their pencil and paper, right? And they come up with these amazing ideas. Fantastic. It's the same idea here. We are mathematically defining in the computer, we are defining what we can do with these objects. Here's like, we can look at the headers basically and be like, here's what I'm going to do with my course. Okay, this is what it can do. But if you don't look at the C++ file, you don't know how it's being done in code. But if I told you that this is what you can do, without knowing how it does what it does, you can imagine how you can use that object in a useful way. And it doesn't matter how it's implemented. That separation of the what from how is such an important idea that I really want to like emphasize it and drill it into you. Is I don't care how my car works, but I don't need to know how it works in order to use it. For as far as I'm concerned, if I've never opened up the hood, maybe it's a whole bunch of magic frogs under the hood and it works. But I don't care. It doesn't matter because I can use this idea abstractly, the car, to solve problems for myself. I don't know how this magic box works in front of me, but hell, I can do a lot of stuff with it because I know what I can do. I just don't know how it works. Fantastic. I don't care how it works. It's that idea. So separating the what from the how is critical. Now, don't get me wrong. When we start defining our stacks, our queues, we are going to also be defining the how. We will be writing that. But the point is the exercise of like, these things are different. Because you might also remember, how many ways are there to solve a problem? Literally infinite. So if I say, I want my collection to be able to do this, this is what I want it to do. How it's implemented? That doesn't matter. It could be implemented of one of a million different, of an infinite number of ways, and it'll still do what it needs to do. And we will see a couple of examples in this class of how we can implement a stack or a queue in two completely different ways, but the functionality, the like what stays the same. Okay, collections, pros and cons. There's no free lunch. Every collection we will look at has pros and cons. There are some things that are awesome about a stack, but suck about a stack. And then there are things about queues that are amazing, but suck also. And in addition to learning how collections operate, we will look at the types of problems each collection is like good for and how we might implement it and what are the pros and cons. ADT, abstract data structure. It's a set of values and the operations defined for that type's values. So integers, operators, right? Abstract data types is a collection of data together. So data types, that's like your integers, okay? And what you can do with integers. Abstract data types, that's like when we have a collection of data. It's like, it's our collections. Stacks, queues, lists, trees, graphs. People often use the word data structure to mean ADT too, but data structure usually means the actual implementation. These are some nitty-gritty semantic details that aren't really that. Don't get too bogged down by that. That's that. Welcome to 162. Now we have a little bit of time left to start introducing stacks. This is our first data structure that we're going to start implementing. Now you might see like, okay, I'm saying stack and then I'm saying int array stack. So the stack is going to be like the more abstract version of what a stack is. And then an int array stack is going to be a specific implementation for a stack of integers, and it's implemented with arrays. So the point of this lecture, we're going to define the stack, use our definition of a stack to solve a problem, and then we will implement it. You'll see that I'm going to say we're going to use a stack to solve a problem well before we actually code it and know how it does what it does, because we don't need to know the programmable how. We just need to know what we can do with it to then make use of it. Okay, stack. It's a collection of elements that are strictly added and removed from one end. This end is called the top. You might say, yeah, but can't we just insert it after? Yeah, you could, but then that wouldn't be a stack. Remember, this is the definition of a stack. You can change it if you want, but then it's not a stack anymore. So last in, first out, LIFO. The last thing in is the first thing out. Last in, first out. For example, a stack of plates. Or here's one, your web pages. If you're on a web page and you hit back, you go to the last page you were at, not the first page you were at. And if you hit back again, you go to the previous one, and the previous one, and the previous one. Our web history is like a series of like adding things and removing things from the stack. You know, I go to this web page, maybe I go back, go to a new web page, go back, go to a new one, back, new one, back, and so on. So here's the old top, bottom of the stack, and now we put this, what I say, teal, turquoise, I don't know. We add the new one, now this is the new top, hey, awesome. And if we wanted to remove something, well, we take that off, and now this is the new top, which was the old top. Popular uses for a stack, backtracking. Your assignment 2 is going to be using stacks, I think. Maybe it's a key. I think it's a stack. Back button for browsers, undos and like word processors. Here's a really good use is, here is a use, is checking if your brackets or parentheses line up, right? So we've got an open, a close, an open, a close, a close. So we can use a stack to test this. And we can also, you know, same thing with like markup languages. And oh, here's one. This is a weird one. Postfix expression evaluation. So, you know, us humans, we like what we call infix mathematical expressions. This is where we say, okay, A times B plus C. You know, it makes sense. But there's postfix, which is this, which is A, B multiplied by C plus. Well, what the hell is this? Well, this is like you would take A and B, multiply them together, and then you take the result and C, and then you add them together. Call stack, runtime stack, functions are pushed onto the stack when called, and they're popped off. Okay. Collection operators. For every collection, we are going to need a way to add something to it, a way to get something out of it. Probably we're going to want to know if the collection is empty. And we're going to want to know how many things are in our collection. And I guess that's about it. I mean, there are other things we can add as well. But for the most part, whether we're looking at a stack, queue, list, we're going to want to be able to add and remove things and check if it's empty, which is, you know, easy, and see how many things are in there. You know, we're going to want to do these basic things. We're probably going to want maybe like an equals and a toString or something too. So for a stack, we have push. This is adding something to the top of the stack. And push, this is the word we use to mean add something to a stack. We push something to the top of the stack. And then we have pop. We pop stuff off the top of the stack. We have peek. This is a different one. This is look at the top of the stack, but leave the thing there. Oh yeah. And then it is against the rules to access anything from anywhere else other than the top of the stack. I know that when you're coding this, when you are implementing the how, you can code it in such a way that you could access more stuff. Absolutely, you could do that. But if you do, it is not a stack anymore. You're breaking the definition of a stack. A stack is a very constrained, simple data structure. So we've got our push, pop, peek, and I guess we'll have is, empty, size, and toString. So this is what we're going to want to implement. But at this stage, this is the what. This is what we can do with the stack. And immediately, if I told you, without, like, you do not need to look at the code to know what this is doing in the abstract idea of what a stack is. You push something, okay, you just keep adding things. Pop, you take them off. Peek, you look, but you leave it there. You don't need to know how it's implemented to know what these things mean and to know how they might be useful for us. So it's just a bunch of operators. It just says what can be done. It has nothing to do with how it's implemented. None of this says how we push, pop, peek, how we store the information and whatnot. Nothing about where we store the data, nothing about how the operators do what they do, and it absolutely has nothing to do with C++. This right here is just as relevant for Python as Java, as C#, as blah, 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 and blah, 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 any other object-oriented programming language. So I guess we're out of time, and we'll pick up here next tomorrow, I guess. But again, I'm really trying to drive in that abstraction and the separation of the how and the what are very important. So anyways, oh, I got a question here. So is it like an object of an object, for example? Can we take the stack and like make another one? I'm not sure what you mean, but I have a feeling you're thinking too hard, or at the very least, the top was about collections. Then put B back on. I don't know. We'll cover this next time. I've got to run to another meeting. Hopefully you learned something. See you all later.